Hi everybody, thanks for staying around for this presentation after 10 minutes of preparing and before lunch to boot. So I'm Gábor Molnár and I'll talk about how you can create flash drives from just ASCII characters. It doesn't seem to be that exciting, but you will see why it still is exciting. Do not believe the handout. This is me according to the handout. But if you know the guy, please present him to me because I don't know who he is. Well, anyway, a couple of words about myself. I work at the KFT and I'm busy doing malware analysis and penetration testing, and I also participate in my free time in bug bounty programs. One of those was Prezi's bug bounty program, about which you could hear a presentation in the adjoining room, but please don't go there now because we are simultaneous. They give you $500 who finds a bug in their web app. And in April, I sat down and checked out their app and actually did find a bug in Prezi. Took me 2 days initially, but then it actually lasted for 2 weeks. And this is the bug I'll talk to you about today. Let me start by saying that Prezi has multiple domains. They have a main domain, prezi.com, hosting the web application, and they have a lot of other domains hosting a lot of other applications. If you upload a file, it goes to a different domain. If you are searching, it goes to it transfers to a different domain, etc. And the web app running on the main domain needs to somehow communicate with the other domain, with the other apps on the other domains. And the same origin policy that they use is actually okay. It ensures that an app running on the domain A cannot request send HTTP requests to domain B. If this is needed, then it must be enforced somehow. And this is done by cross-origin resource sharing. This is a standard that is supported by all browsers and is everywhere. The problem was that IE6 did not. Instead, they came up with the JSONP. Not they. JSONP was used. Because of the same origin policy, you are not allowed to read HTTP requests coming from another domain, but you can run that request. So I actually pull in a script from the target domain, it runs, and it passes information to my JavaScript code. This is what it looks like in the web app. First, we define a function that will receive the response. Then with the script tag, we pull in the URL that hosts the API, and what is returned by the API is shown in the Randry frame. This is the entire HTTP request, but only the bottom line will run as a script. It actually calls the function we defined and pass data to it. We actually bypass JSONP, and this is why Prezi actually also uses this approach, so it can handle older browsers as well. What will be important for us is that in order for the JSONP API endpoint to know what function to call, it needs to receive our function name in a parameter when it is being called. This is where you can see it. And another aspect of JSONP APIs, Prezi want to make sure that search.prezi.com cannot be accessed by just any old web app, because otherwise sensitive information could be leaked. So they use CSRF tokens. The CSRF token is a shared secret between the main domain and the API domain. And when the web app running on the web domain issues a query, the API always checks whether the target sheriff token actually is appropriate. This was the first bug that I found. Some apps did not check this token, which means that I can actually send JSONP queries to Prezi from any domain. This was not yet interesting enough. Some more research was needed to get at interesting results. So I started working on how to further develop this attack. And I found that we could try this, specify anything. You can specify anything for the callback name because it'll return it. And what if I specified an HTML code as the callback name? The API domain will return it unchanged as the callback name. And I put it in an iframe, not in a script, but in an iframe tag. And I want the browser to interpret it as HTML. This is good for me because I'm actually running a JavaScript code, my JavaScript code, in their domain context. So the code that I specified will run in accordance of their domain rules. So it will read, for instance, Prezi.com's cookies. But as it turned out, it doesn't work because in each HTTP response, it includes the resource that the web server returned with, and the web server always returns the statement that it's a JavaScript resource, and for this reason, the browser does not display it in an iframe as an HTML, which is absolutely correct. But this foils my first attack attempt. After further work, I noticed that the JSONP endpoints return the callback name in an interesting manner. In front of the callback name, they enclose an empty JavaScript comment. Doesn't do anything. When you call the API, it will be validated as a JavaScript comment, and it will do nothing. And I found on Stack Overflow that somebody was asking why this is so, and the Facebook engineer gave an answer. He said that an attack scenario is imaginable that resembles XSS, but is not in fact XSS, but Flash. This brief HTML code snippet shows what I'm talking about. So the essence of the attack is that as callback, we specify a Flash file. When the API responds, it adds the callback name at the beginning, which it thinks is a callback name, but it is in fact a Flash file. And in Flash embedding, the browser does not take into account the content HTTP header. In the object tag, you see that I tell it to interpret it as Flash and to ignore the content type header. And the browser actually did run it as a Flash file. Why is it good? Because Flash files also are subject to the same origin policy. In this case, if an attacker website embeds such a Flash file, that Flash file will run on Prezi's domain and will be able to access, for instance, Prezi's cookies, or can send HTTP requests to Prezi's domains without any restrictions. So this is the attack that they wanted to avert using this empty comment. The response will not start with the byte sequence that you specified, but with the empty comment. But JavaScript doesn't care about this, but the Flash interpreter does. If it becomes an invalid Flash file, nothing will happen. This is the essence of this empty comment. And this is where the second Prezi bug comes into play. The empty comment is missing in some JSONP APIs, so I started to create a proof of concept. And I immediately encountered this restriction. In most web pages, the callback name cannot be just anything. It is restricted to the O to 9, A to Z, lowercase a to Z interval, so only ASCII, alphanumeric characters can be included. Prezi was more relaxed. They actually allowed the lower half of the 8-bit ASCII table, part of which obviously is more than just alphanumerics. It includes 0 byte and 1 and 2 and 3, which are not included in the previous set. And as it turned out, one of Prezi's people told me that these were Django-based APIs, and this is how the callback name filtering works, but Haskell allowed anything. So anybody who found this Haskell API endpoint and sent it a flash, got it back, returned to him unchanged. So I started working on this flash file that needs to fit into the lower half of the 8-bit ASCII table, so only characters below 80 hex can be used, and I found that this is not that difficult to solve. There are some restrictions that you need to adhere to, but if you do that, you will not run into any problems. If the file size is 255, that is not okay, because coding it on 8 bytes will contain FF, which is an invalid character in the lower ASCII half. But if 256 is the file size, then the first block will overflow, and this will result in an ASCII value, in a value that is within the restrictions. The second thing is the bytecode that must conform to rules, to the same rules. But I found that most of the bytecodes, or most of the opcodes, are in the lower ASCII table. Some don't. Unfortunately, jump, for instance, is in the upper ASCII table as a code. If you created cycle, then in Flash the cycle is run, and you jump with a negative value to the start of the cycle, and this negative jump usually contains FF bytes because the offset is stored as 4 bytes, and obviously negative numbers start with FF in hex. So you can't use cycles, but you can solve the task without using cycles. Due to these restrictions, I thought about just creating a loader, a minimal loader, as minimal as possible. And once it is run, it should receive the actual flash file from its environment that it needs to load, and then load it. The loader can only be just 5 lines, should not contain a cycle, match the restrictions, and be able to load any flash file that can then do the useful work in parentheses, in quotation marks. This is implementation. There's no cycle. I replaced it with recursion. This had to be solved by, well, it actually reads this external internal interface with object ID parameter, which is actually the name property of the HTML object tag, then parses it by 3 bytes, by byte triplets, puts them in the buffer. First of all, converts them, each byte triplet to an integer, then loads it in a buffer, and it then loads the buffer as a flash file. And this is the code that allows us to exploit this vulnerability. This is the way to start the attack. In the name parameter, you see the actual flash file that needs to be loaded, and the URL includes the loader. I was very happy to be able to implement the attack, but then it turned out that Chrome and Firefox has a bug, both of them, that doesn't allow my hack to work. In Flash file URLs, 0 bytes are not allowed, and this is a bug because a web server allows 0. I may allow it or may not, I don't know, I haven't tested it. If it is not allowed in Chrome and Firefox, then it has no value as an attack. So this is what I did. I wept bitterly, And then I started on working further. I started researching why there must be a protection against something you can't implement. So I found the initial publication by the Facebook engineer who actually answered the Stack Overflow question I mentioned before, and he used some tricks to get there. He was able to put a flash file into a range of 3A to 7F, but the flash file doesn't do anything. It's just a proof of concept flash file. It doesn't do anything, but it does meet the restrictions that it should be 0 and 7F without including any zeros. But this is not enough because this flash file doesn't do a thing. We need a flash file that actually does something, a loader, for instance. So why not do it in this interval? If I am able to put together a loader in this interval, then it would work not only for Prezi, but practically everywhere where JSONP API is used. So my goal was to create a flash file that only contains alphanumeric characters. This is not possible with uncompressed flash files, but there are compressed flash files compressed with zlib or XF. And I was hoping that the compression algorithm can be tuned to the point where only ASCII characters are included in the zip. I picked zlib, maybe SZMA would have been easier, but I started with zlib. Zlib is just a container format. It has the length at the beginning and checksum at the end, and in between it uses the Deflate algorithm, and this Deflate algorithm had to be tuned to meet the constraints on the values. So I checked the standard, and it turned out that there are 3 types of possible blocks. All Deflates contain blocks. One is uncompressed block with the data unencrypted. If you have an encrypted data, you don't want to you want to compress it again. This is the reason for number 1. The second possibility is a Huffman coded block with predefined dictionary, and the third is a Huffman coded block with explicitly defined dictionary. In versions 2 and 3, you can actually use callbacks. Excuse me, back references. If you have a longer byte sequence, you can insert a back reference and say that repeat the byte series before me 15 times. These were the alternatives. I actually found that I can't use 3 of them. I won't be able to use uncompressed blocks because they use 4 bytes to store the block length. And once again, it will probably contain 0 or the length should sprawl across the 4 bytes, which would be a huge size. The second possibility could not be tuned because the dictionary was predefined. In 3, I actually didn't find any reason for my trick not working, and I didn't use back references because it would just add complexity, and hopefully I can manage without. So I continued studying the standard and studied the Huffman encoding. The dictionary is actually a Huffman encoding table, and Huffman is a very simple algorithm, compression algorithm. You have the possibilities for the input bytes, and you assign a code to each of them, which will constitute the bits that may appear on the output. So if the input is the letter A, the output should have 100. The left side symbols are 8-bit, the right hand side is 3-bit, and this is actually the essence of the Huffman encoding. Here you see an example. This is a decoding, and this is the string, this EAD that you receive for the given input. But you see another code at the end. This is the end symbol. The end symbol is a separate symbol in this table, and it shows that parsing can now be finished for this byte stream. Let's look at how we define a Huffman table, and in order for this to be compact, you need input symbols to be sortable. If it's about bytes, then they are sortable, obviously. Also, we need to assume, or we must say, that output codes that are shorter should be listed before the 4-bit codes. In this table, you also see that 2-bit codes always start with a 0, but 3-bit codes always start with a 1. So 2-bit codes are nearer the beginning of in a sorted list. Also, if the code length of two symbols is equal, then the symbol that is before the other one should get a code that is before the other character's code. Well, after specifying all this, it's very easy to encode a table because you only need to store the length. Sort the table by symbols and store the lengths. Once we have it, we can look at how we create an ASCII from this. The basic idea is that, no, this is in more detail the compressed block. The end, it has the compressed data. The Huffman table for it is specified in the preceding table, which need to be compressed into the table before it, and its length is specified in the header. This was a bit complex, so I had to do a lot of manual work with paper and pencil to find out how I can create ASCII from it. The plan was to first define table 1, then see what table 2 should be. Let's define table 1 such that it should assign to all symbols of the compressed data an 8-bit ASCII output symbol. So if the input only 3 types of bytes can occur, then we should assign the letter codes A, B, and C to the output. Once we have this table definition, we can deal with table 2, how to define it, to have also table 1 definition on ASCII only. This limits the size of a block because we have a finite number of ASCII bytes, 62 different byte values, and one block can only have 62 different types of input blocks. If we reach 62, we need to start a new block. Also, in Deflate, bit order is reversed. Everything needs to be interpreted from from right to left, and it's not so we have also to interpret the restriction in reversed form. And this is the most complex thing. We define table 1. Okay, on top you see the input. 1, 3, and 8 is the input. And this will generate the 8xd0 output. 0 is the end of block. So you have to assign 8 to the input 1, X to the input 3 and D to the input 8. Let's assume that the first 8-bit code will be 0001110. So we define lengths by having 8 for length, for the length of 1, Jesus, for the 3, okay, if we also define an 8-bit code for 2, which we won't use, then we'll arrive at X for output for 3, which is also okay. This is actually a crafted input, because if it was a different input string, I would not be probably able to have only lower ASCII in the output. And but I can then start a new block and then solve the problem. The next ASCII code will be D, interpreting the bit sequences in reverse order, which means that between 3 and 8, we need to define 3 different 8-bit long codes to arrive at D as the output for 8. And we can then also define the end symbol. I'll explain the blue and the red color later on. So you define a lot of superfluous 8-bit codes, and you do this to get an ASCII code for the end symbol. The first valid 8-bit code is the one that we assign to 1. We actually define 6-bit codes, which will not be used. They are only defined as space fillers before the first 8-bit code, because we assume that always the shorter codes will occur sooner in the alphabetical sorting. And finally, the red part means that we need to define further superfluous 8-bit codes to have the table complete. We should not have an input where no output is defined. Once we have this, the compressed data will be ASCII only, but this is the table definition of table 1. We compress table with table 1, and it also must be ASCII only. All codes are 0, 6, or 8, so table 1's input will only consist of 0, 6, and 8. The trick here is that we need to set up this table such that we assign 4-bit codes to these inputs, and these 4-bit codes must be such that in whatever sequence I order them, they will yield ASCII characters. The compressed representation of the second table should start at a 2-bit offset, and the 4-bit codes, well, maybe you don't see it, but if you start paper and pencil, you will see that ordering these 3 codes in whatever reason in reverse order, you will always arrive at ASCII characters interpreted from the left-hand side. So that was the basic idea for the second table. And also we must ensure that the table 1's definitions must also be ASCII, but we have a lot of freedoms for that because the holes between the values can utilized for practically anything. The further details are included in the code if someone is interested. What I just told you This is the first half of the game, because this was an algorithm that works for any input but generates large output, because if you have byte 1 and 2 in the input, you cannot define a table because they are neighbors, so you need to open a new block, but the blocks table definition part is very long, so you have a lot of wasted bytes. Therefore, there is a second algorithm that is much more optimized, but is not able to compress all input, only most inputs. So you can use these two as needed. When I had the algorithm, all I had to do was to write the loader. This is the final ASCII flash loader. I could now use cycles, and this is the file I arrived at, which is the holy grail of ASCII flash files. And using this file, you can load any flash file in the following manner. You need to specify in a callback the ASCII flash file you generated beforehand, and these 4 parameters will be read to arrive at the file that need to be loaded, and this file that need to be loaded can be anything. So this is a flash-based access for any JSONP endpoint. I was once again very happy, and then it turned that Prezi fix the CSRF token bug. So what about other websites who are vulnerable? Not a bad list for an attacker. So what do I do now with this problem? I wanted to announce this bug. There were 2 alternatives in front of me. One was the Internet Bug Bounty initiative, which is about announcing flash bugs, or generic bugs that affect a lot of websites. And in this case, they help you coordinate the notification of those affected websites. Here, there was a chance that Adobe won't fix it, because if it does so by not processing flash files with the junk at the end, so it doesn't process. If it doesn't process files where there's junk at the end, then it'll probably break the flash files of half of the internet, because probably most flash files end with junk. So they may say they will not fix the bug. There have been occasions, there have been events like this where they didn't fix a bug due to backward compatibility. So I announced it to Sandbox. That is for generic problems. And it was a very slow procedure. First off, I had to wait 2 weeks for the first response, which says that, yeah, it qualifies for a bounty, and if it affects a lot of sites, let's coordinate the notification of these sites. And I replied, why not interpret Adobe first, and if they don't fix it in Flash, then we start to notify the other web pages. I waited 2 months. When I saw an article by Michele Spagnuolo from Google, who published exactly the vulnerability that I published, and I saw that he actually stole my idea using the same Huffman table. This is how he got the information. He actually noticed the ascii-zip project, which I published, thinking that nobody will care about it. Who cares about an ASCII-based zip compression algorithm? But he actually did read it. He knew about this vulnerability that was published by this Facebook engineer, and actually he put the two together and re-implemented a tool which is called Rosetta Flash, which compresses any flash file into such an ASCII flash file. His approach was not to create a loader, he created a compressor that works on any flash file. That was the only difference. And he also submitted to the Internet Bounty, but he selected Adobe, and Adobe fixed the problem very quickly, updated the Flash PR. And within 1 week, he announced it. He actually published his tool, the Rosetta Flash. And all this happened 3 months after I submitted the problem myself. And it all got a huge media hype. The Rosetta Flash, the happy end is that Michel and I both received a $3,000 bug bounty. Adobe fixed the bug, and everybody is now safe.
És akkor néhány Google mérnök nem pont ugyanő, hanem egy pár másik.
Some Google engineers, not him, but some others actually reverse engineered the fix. And to shorten it, they first check the flash file whether it includes a character that is not JSONP compatible, and it is only run if it is not JSONP. If it is not JSONP compatible, then they quickly saw that this is very easy to circumvent. The only thing they need to do is to have the check byte at the end of the JSONP file to be a closing parenthesis. If you send it without the closing B parenthesis, then the recipient will add the opening address, so you will end up with a flash file that is not JSONP compatible.
És emiatt így nagyon egyszerűen megkerülhető a probléma. És akkor jött a rendes megoldás, ami abból állt, hogy egyrészt nézzük meg ezt a content type headert, ami az egész problémát okozta. Ezt igazából nem is tudom, hogy miért nem ezzel kezdték. És másrészt nézzük meg minden byte-ra, hogy nagyobb-e, mint 0x80, az ugye tehát magyarán nem csak azt ellenőrzik, hogy JSONP kompatibilis, tehát hogy ne legyen JSONP kompatibilis, hanem egyáltalán ne is legyen ASCII. És hogyha van legalább egy ilyen byte, akkor átengedik és mehet. És tulajdonképpen ez egy tényleges megoldás volt. Köszönöm a figyelmet!